I'm Ken Gallock Yoshimura from Kyushu University in Japan, and I'm going to talk about a quantum heat engine driven by quantum fields. So this talk is based on my two recent papers, one of which is published in Frontiers, and the other is I posted online today, so you can go check out with this archive number. So this project is about something called a relativistic quantum Otto engine. So to begin with, let's go to thermodynamics. And we all know that in thermodynamics, the main topics is the heat engine. So the famous one is the Carnot engine. And Carnot engine is the four-stroke heat engine with isothermal and adiabatic processes. Right? And you can extract work from this. Now, in recent years, people are very interested in combining thermodynamics with quantum mechanics. So if you do this, you get something called quantum thermodynamics. So for example, you have a qubit, and qubit might be immersed in a thermal bath, and you can examine how qubit extract work or exchange heat with the thermal bath. Now, also in quantum thermodynamics, you can consider something like quantum heat engines. For example, quantum Carnot engine and quantum Otto engine are very popular engines. And in particular, quantum Otto engine is our main topic here today. And this engine is basically four-stroke engine with two adiabatic and two isoclic processes. And it is very popular because you can compute heat and work in a separate manner. So it's very easier to analyze the exchange of energy. Right? So far, these engines are in the context of quantum thermodynamics, and typically people consider in the context of quantum mechanics. Now, one might ask, what happens if you introduce quantum field theory? And in this case, your qubit is now immersed in a quantum field. And this was first considered by these people in 2018, where they considered a qubit traveling in a space-time and interact with a quantum field. So your quantum field is now acting as a bath, and they show that you can extract positive work by using the induced Unruh effect. So by Unruh temperature, you can actually gain work from this. So in our project, we are basically considering qubit in quantum field theory and generalize this work in a sense that we are considering qubit's trajectory to be arbitrary time-like trajectory, so it doesn't have to be like a linear acceleration. And also field state can be arbitrary quasi-free, meaning it doesn't have to be Minkowski vacuum, but you can also think of like thermal state or quasi-free state, squeeze state. And also background space-time can be arbitrary globally hypergolic space-time. So, like a black hole space-time and so on. So this is the general background idea of project. And before going to detailed results, I'd like to talk about the quantum Otto engine. So in the mainstream quantum Otto engine, people consider like qubit or harmonic oscillator. And in this case, let's consider qubit with energy gap omega 1. And the initial state is prepared to be something like this. Okay? Then you expand the energy gap to larger value omega 2. And in this process, you're considering like adiabatic process, meaning there will be no heat exchange between qubit and thermal bath. Now, you put the qubit into the thermal bath and thermalize with it, so that in this process, the energy gap is fixed, so this can be considered as an isoquadratic process, and the heat will transfer from the heat bath to qubit. Right? And you take out the qubit and again compress the energy gap to the original omega-1 value. And then you again immerse the qubit into the colder heat bath so that your qubit will release heat into the thermal bath until the point where the qubit state becomes the initial state, something like this. Right? Then people show that from this process, you can actually extract positive work. Okay? Now, in our paper, basically we want to extend this to quantum field theoretic point of view, in the sense that the heat bath is no longer just a heat bath, but it is a quantum field in an arbitrary quasi-free state. So it can be like a vacuum state, thermal state, or squeeze state, and so on. And trajectory can be anything. And also, it doesn't have to be like a quasi-static process, meaning your interaction between qubit and quantum field can be like arbitrary time dependence. Okay? So this is our setting, which is very general. And here is a table of our result comparing to the traditional quantum auto engine. Okay? So in the traditional quantum auto engine, the assumptions were the qubit contacts with thermal bath, right? And also, the way they contact with the thermal bath is quasi-static processes, meaning they interact for sufficiently long time so that they can thermalize with it. Now, in our case, we're basically generalizing this assumption to something like this. So the qubit doesn't have to be interacting with the thermal bath, but instead it can be quantum field in arbitrary quasi-free state. Okay? So this includes the thermal bath, thermal state, and also the quasi-static processes is now instead considered to be a anytime dependent interaction. So it's like the time dependence of the coupling is arbitrary. And also, because we are considering quantum field theory, we are looking at global hyperbolic space-time and the trajectory of the qubit being like any time-like trajectory. And then we can compare the results. So the claim of the traditional quantum auto engine is that if you do that cycle and try to extract positive work, then the condition to obtain positive work takes this kind of form, where omega-1 and omega-2 are the energy gaps of the qubit when they are immersed in thermal bath at temperature Tc and Th, respectively. And if you compute the efficiency of the cycle, then it is known to be something like this. And if you substitute this condition, then this efficiency has the upper bound, which is equivalent to Carnot efficiency. So Otto cycle cannot go beyond Carnot efficiency as long as this traditional quantum Otto engine is concerned. Now, in our case, we can also consider positive work condition, and we can mathematically prove that the condition takes this kind of form, where my temperature is no longer actual temperature, but it is something called effective temperature observed by the qubit. So effective temperature is something like a fictitious temperature, and it is determined by the response functions, meaning response function is something like a transition probability between ground and excited states. And also, we can compute the efficiency of this cycle. And it turns out if you substitute this inequality here, then it is no longer Carnot efficiency, but instead, this can be considered to be generalized version of Carnot efficiency. So our setting gives very general results, and as a special case, it has the previous traditional results in the sense that if your quantum field is in thermal state and the qubit interact with the thermal state for sufficiently long time, then your effective temperature becomes the actual temperature of the bath. So the previous traditional result is the special case of our result. So this is the main point in our paper. And finally, I want to talk about today's paper that I put online here. And previously, as I mentioned many times, our assumption is very general here, right? So like quantum field in arbitrary quasi-free state, global Habitable space-time, any timeline trajectory, and so on. Now, I didn't mention this before, but we used perturbative method, meaning I assume the coupling constant between qubit and the bath is very weak so that I can use Dyson series expansion. Okay. Now, instead of having these two assumptions, I can also consider something like instantaneous interaction. Okay? So everything before is the same, but the time dependence of interaction is considered to be like very quick. So this is like a Dirac delta kind of interaction. And it is interesting because instantaneous interaction in the context of quantum thermodynamics is very opposite of what people do, because usually people consider like sufficiently long time interaction, but we instead ask, what happens if I take instantaneous interaction? And also, by employing this interaction, I can use non-perturbative method, meaning I don't have to assume coupling constant is very weak. So intuitively, here is a space-time diagram, and the two isochronic processes are now instantaneous. Okay. And we can ask, can we extract positive work with this kind of instantaneous interactions? And in this archive paper, we said yes, we can extract positive work as long as the first interaction affects the second interaction. So meaning here is a space-time diagram, and when the qubit interacts with the field for the first time, the qubit will disturb the quantum field, and this disturbance will propagate, for example, at the speed of light in Minkowski space-time, for example. And my claim is that if the second interaction is affected by this disturbance of the field, then you can extract positive work. But otherwise, if the second interaction is not affected by this disturbance, then you cannot extract positive work at all. So in summary, we considered quantum thermodynamics in the context of quantum field theory, and by assuming very general setting, we show that we can have very generalized version of traditional quantum auto engine, as well as very ridiculous setting but very interesting results with instantaneous interaction. So thank you very much for listening.
All right, perfect. Are there any questions for Ken? So you can just unmute yourself and raise your hands. Well, if not, I do have a question. So, Ken, you've been considering this coupling, which is basically the UDW coupling, I'm assuming, right? So you're coupling to the field itself.
Yes.
To the amplitude.
Yeah.
Now, what I was wondering is, because if the field is in a KMS state, if the field is KMS with respect to the notion of time evolution of the detector, then whatever you get will be whichever result you get will be independent of which field operator you couple to, simply because the KMS condition is satisfied, as per its definition, right? The KMS condition is valid for all observables, for all operators, right? So it's a condition over the 2-point function. Have you, in your case, you're considering more general classes of states and of trajectories? You're not really only looking at the KMS, you're not imposing this KMS. So have you looked up to which extent your results depend on whether you couple to the field or to its momentum or to the derivative of the field or something like this? Have you explored this?
Oh, okay. Well, first of all, it doesn't have to be like KMS, in the sense that, like, if your Weidman function doesn't satisfy KMS condition, then, but still you can, do the same thing and calculate the positive work condition, right? In that case, it will be effective temperature, but there is no KMS temperature limit, if you're asking something like that.
Yes, but then it's going to depend on many things, right? It's going to depend on which operator you couple to, on how long you couple for, it's going to depend on the energy gap. It's going to depend on a bunch of things, right? So basically my question is whether your results depend on, because you're varying the energy gap in order to implement these things, but does it depend on whether you couple to the field or to the momentum in this case?
Well, it definitely depends on, the way we couple to the field. So the final, but the point is, the actual value will depend on the coupling. But the point is, your positive work condition only cares about effective temperature. So, if that answers your question.
Yeah, no, that's amazing. But you should definitely take a look at whether this effective temperature depends on which field operator or observable you couple to. That'll be an interesting exploration, I guess.
Sure.
All right, cool. Thank you very much, Ken.